Oh, okay.
Yeah, I actually got married a few weeks before I started these courses.
Wow.
All right, guys.
Congratulations.
Thanks.
All right. And I think there's a couple folks on are getting on board on Zoom. We got Otto here, and Mike has agreed to come and talk to us today. Mike brings a lot of experience in software development, working for all kinds of companies, from Intel, Hewlett Packard to more interesting companies like Andrews Cooper, doing stuff from Ray-Ban to other groups and all. 3D glasses, what's it called? Augmented reality glasses.
Yeah, augmented reality with Meta.
Big Meta, so Big Meta and other things. So I'm gonna turn it over to Mike to add to whatever I didn't get to, and also start us off on the topic he's chosen to talk to us about.
Thank you.
And this is getting recorded for folks, so you know.
Excellent. Well, I hope everybody can hear all right. As you said, today I'm talking about designing a serial communication stack. And along the way, we're also going to have a little fun with AI. I decided to use AI to do all my graphics for this presentation. That's the first time I've done that. And we had very mixed results with that. It'll be kind of fun to see how the AI responded to all those things. A little bit about me, as Izad said, I've worked in the technology industry for a really long time. In fact, when I went to go to my undergraduate school, they didn't have a computer science department. They had a math department, and you got a computer science focus in your math degree. So I have an undergraduate math degree, but then I went on to graduate school in a computer science department. So I'm not going to say what year I graduated. It was a long time ago. The college I went to, their science building had a mastodon in the front entranceway. A mastodon's a woolly mammoth. You guys probably know that. And of course, not a live one, but I think it had probably died a year or two before I got there. Preserved it right out in front. So yeah, the dinosaur stories and the back in the day stories will roll freely here. All right. So serial communication. So why are we going to why use the serial port, right? We've got Bluetooth, we've got Wi-Fi, we've got lots of other things. So the first reason is because it's easy. Almost every, I'm going to be talking mostly in the context of embedded systems. So small devices talking to a host computer or small devices talking to each other. So most MCUs these days have a serial port, at least one serial port built in, maybe multiple serial ports. The stack that you need and the programming that you need to utilize that serial port are pretty minimal. So that's one big reason why we would use a serial port. It's also cheap. It comes with the MCU. The MCUs are really cheap these days. Whereas if you're talking about, say, a TCP/IP network stack, it's much harder to get a software stack running in your MCU. It's much more resource intensive. It's generally more expensive in terms of external hardware that you need in order to make that work. So easy and cheap. So easy a caveman could do it. So when I put this into my first AI, I said a caveman working on a computer. And the first AI said, I can't do that. I said, well, why not? It said, well, that's misleading. Are you serious? So I tried a different AI, and the other AI kicked out a caveman on the computer. It didn't care about being misleading. All right, so what are we going to be talking about here? So this is a device, and the first thing we'll be talking about is use cases, like what do we use serial communications for? Cover that. And then this terminology, the data link, the physical, the presentation, and the transport, these all come out of what's called the OSI 7-layer model, which is something that you probably want to look up on Wikipedia or something, get a high-level view of it. And it's basically an abstract description of the layers in any sort of computer communication, mostly in a network context. A lot of these layers are kind of abstract and wishy-washy, but if you just kind of get the idea of it, it's pretty helpful, and it's used a lot in the industry talking about that. So we'll talk about the physical layer, which is the voltage going across the line, and the data link, the waveforms and such. We'll talk about the presentation and the session layer, which are how we package data into packets to go across that wire. And then we'll talk about an application layer, how the other side kind of interacts with that data when it comes across. All right, so let's see the use cases. So this is an AI picture. I don't know what that is. Anybody ever seen a plug like that? I've never seen a plug like it. Was supposed to be like an Arduino connected to a computer with anyway. AI went a little crazy there. Didn't quite capture it, but it's not too bad. I mean, if it's blurry and you look at it from a distance. Okay, so the use cases, like where do we use serial communications? So the first is a bootloader. Do you guys know what a bootloader is? If you had any experience with that. So in the old days, we used to have to we'd have a board with a MCU on it. We'd have to take that MCU out and we put in a programmer. And that programmer would program the flash memory or some sort of non-volatile memory on there. And then you put it back in the board and it would work. And then when you're ready to go to production, you'd get rid of that big removable socket thing and you just put it on the board. Which is kind of a pain in the butt for every time you want to write a program, you got to pull it out, put it in your programmer, and pull it out, put it back. So the concept of a bootloader came up where you take it out once and you put it in your programmer, you put a little program in there. And that program talks over a serial port or some sort of communication device, and you can write a program to it, and they'll stick the program in memory and then start executing that program for you. And maybe there's a little button on there that lets you break back into the bootloader when you want to load a different program on. So you don't have to remove that out all the time. So that's what a bootloader is in an embedded space. So it's a much easier model. There we go. Host device control. If you've ever used an Arduino or something like that, you want to send commands down to that device. The device does something and it sends some information back, some telemetry or something like that. So debugging a device. You've got this device out there and you want to know what's going on inside it. There's no screen usually. So how do you know what's going on in there? What's it doing, right? You can blink lights. It's a little bit. It can help. We often have blinky lights on these low embedded devices. But for debug and also for logging, you want to know, even in production, you might want to know, hey, okay, I finished a part, or something like that. So logging. The Mesh-tastic devices, I don't know if you guys are familiar with Mesh-tastic. It's a little radio unit. I got one the other day and I hooked up. One of the first things I did was hook up a serial port to it to see the packets that were coming in and just kind of try to understand a little bit more about how the network transactions worked. And the last reason is for testing. You're designing a device that goes out in the field. You want to inject certain circumstances or errors and see how the device reacts. It's kind of a subset of the device control, but it's, you need to be able to test that device and, figure out if it's gonna work in different circumstances and, having a serial link is a good way to do that. All right, so, other use cases are, inter-device communications. So this is one of the AI ones that turned out really good, actually. I thought, I told the AI, I want a robot and it's got a mechanical motor part and it's got kind of a control head part. And it actually drew something pretty good there. So inter-device communications, an example would be, I worked on a robot at one point. It didn't look like this, but it did have that kind of separation. It had a main CPU board and it had a motor control CPU board. And we use robot operating system in which you have these streams called topics. And it's just a stream of data. And the way you control the motors is through what they call the twist stream. And the brain, you would tell it, I want you to rotate 90 degrees to the left. And then it would send individual motor control commands down through this stream to the motor control device down here. And it would pull those out and interpret them to figure out how to do a wheel differential to rotate 90 degrees. So that's inter-device communication and smart sensors. So something like a GPS, right? If you have a GPS, it'll tell you like got so many satellites. I'm at this location. I'm reading that you're at this location. Stuff like that. And it'll send that out over serial link. There's lots of smart sensors now. Basically, they have an MCU embedded in them as well. So it's another special case of inter-device communication, but smart sensors is a good use case for serial devices. So I have a couple of design rules in here, 4 design rules. The first one is determine your use cases up front. A lot of people go, and the reason for this discussion is because I've seen so many really bad serial setups, and it just is really frustrating for the user. As a programmer, they break down. So be realistic and include all the use cases. Figure out what use cases you're going to want to use up front, and the comm link shouldn't be an afterthought. They're often an afterthought. Somebody will go, hey, we need to test this. Oh, okay, let's use a serial link, right? It's kind of an afterthought. Think of that stuff up front. There's no reason not to. All right, so we're going to move on to the physical data link, or the physical data link, which is the lowest level within a device of these kind of software stack. All right, so here we go. So what am I talking about? Serial communication. So it's 1 bit at a time. It's binary, so it's either so in the official spec they call it mark or idle, or mark or space, which is 1 or 0. It's binary. It's asynchronous, which means there's no clock signal going across between the 2 devices. They each run their own clock. They know what speed this data is supposed to be coming across, what that frequency of 1s and 0s is, but they haven't synchronized their clock. There's no contract there or anything. So that's what asynchronous means, and it's point-to-point communication. So it's not a bus. You're not talking to 5 devices on a single communication. And if you go to really nail this down, every single one of these is a lie at some point. So 1 bit at a time in binary. There's we were talking earlier about modems. So modems convert a digital or binary stream into audio signals essentially, or frequency signals. And then decode it on the other side. They're often sending 3 or sometimes 4 bits at a time as a single thing down that wire. Binary, obviously an analog signal, like on a modem, it's not binary, right? Asynchronous, there's definitely serial devices that also have a clock wire that goes across that says, okay, now I'm clocking in the next bit. Right? And point to point, there's definitely serial buses. We were talking about I2C and SPI buses are all serial buses. But for the most part, when we talk about a serial port sitting on an MCU, it's this. I'm having a little trouble with my clicker. There we go. Okay. I'm sure you've all heard of baud. So the baud rate is the rate at which we send a symbol across the wire. So each one of these kind of squares here would be a symbol. And in order to do a robust communication link, we have to send more symbols than you're sending data usually. So in serial, the very common extra bits are things like a start bit. So you can see like you have a high to low edge that indicates, okay, I'm going to start sending you something. And then you have to wait a little bit before you can start sending the data. And then you'll have a stop bit. That'll be a high to low transition that'll say, okay, I'm done sending that packet of information across the wire. So when you're sending data, you know, this has 8 bits here, but we're actually sending 10 bits in order to send that 8 bits. So you're not getting the full bandwidth, but the baud rate is the signaling rate, how many of these you can send in a second, essentially. So common baud rate for serial lengths is 115,200, 115.2. I think that's about 8 microseconds. Yeah, it's a little more than 8 microseconds. 8 point something. Let's see here. Okay, you might have seen this hooking up a serial port, this 8N1. So 8, you might guess, well, looks like we have 8 bits of data here we're sending. This is the most common setting for the configuration of your serial port. So 8, you've got 8 bits. So this is how many data bits you're sending. The N is a little confusing. We'll get back to that in a second. And the 1 is how many stop bits. In the old days, they used to send 1 or 2, or I think there's even a 1.5 bit setting for stop bit. It's weird. A lot of serial stuff is weird because it's really old. Things didn't work as well back then. Now things are pretty well ironed out. But in any case, this is how many stop bits you have. And the N is parity, which is an error detection. It doesn't correct errors, but it'll tell you if there's an error. And the N means no parity. So if there's like 8 or 9 options for the parity bit. So if you say I want an even parity, what it does is it adds another bit in here. So you'd be sending 11 bits now instead of just 10. And it counts up the number of ones in here. And it sets this bit to make the number of ones even in the word. So every time you should get an even number of ones. That's what the parity bit does for you. So if you get on the other side and you count up the ones in there, including your parity bit, and it's not an even number of them, you know something went wrong. In modern serial communications, I've never seen really an error come across a serial line. Like It just doesn't happen, and we're clocking at really high rates. I mean, we're really buzzing. So usually people set this as no parity, like we don't care. It's not going to happen. So, but anyway, if you see this 8N1, that's what we're talking about there. All right. Let's talk a little bit about what kind of tools you can use at this layer, the physical layer and the data link layer. So the first thing we want to talk about is hardware UART. So UART stands for Universal Asynchronous Receiver Transmitter. So it's just a little hardware device that is designed to receive or transmit serial data, and it'll sit there, it'll read in 8 bits or however it's configured. Sometimes it's 5 bits or 6 bits. Why would somebody want to send 5 bits in a chunk? I don't know, but it's a thing. So you read in the bits, and then it'll say, maybe it'll send an interrupt, or maybe you're polling it for a bit to go high and says, okay, I've got some data for you. And you grab that 8-bit byte chunk out of there. So it does a lot of the work for you. And the other option is bit banging, where you have to sit and watch that wire wiggle up and down. You got to figure out what clock are we in, where are we at in this. You got to sample it basically multiple times per bit. To figure out what's going on there and reassemble that in memory. And it's kind of a pain. There's sometimes you have to do it. Sometimes the hardware guys screw up on their hardware, and you have to write. I've had situations like that. So you have to write some bit bang code to just send it out. All right. So it's bit bang is a software implementation of serial comms. The MCUs usually have a library that you can use to implement serial communications. It's usually pretty straightforward. DMA, do you guys know what DMA is? Direct memory access. It's when a piece of hardware with usually within the MCU. So in this case, the UART has access to the memory. So it can clock in the first 8 bits, stick it in memory, clock in the next 8 bits, stick it in the next memory. It's got just enough logic to be able to step through memory and put the things in there for you. It saves you a lot of like all this interrupt, all the ISRs and the polling, however else you do it. It's usually really fast. It saves you lots of clock cycles and stuff like that. And then a ring buffer is a common mechanism to use. So you're bringing this data in. If you know what a ring buffer is, it's just a buffer where you keep track of the start and the end, and it just wraps around. And you just have to make sure that your end never crosses your start, because if that happens, you just overran your data, which is something you see quite a bit in these implementations. All right, so when was the last time any of you guys saw a serial port on your laptop computer? It's been a while. I know you've seen one. So they used to have a little 9-pin port called a DB9, used to be on there. Before that, you had to put in a card. It was usually a parallel bus that you'd use to get data in and out. You got one there. Yeah, there you go. You don't see them very much anymore. So, but we do have USB. What does USB stand for?
Universal Serial Bus.
Yeah, so it's a serial, but it's a bus. Okay, so it's not quite what we're talking about, but there are these translator devices. Sometimes they look like this. Sometimes they look like just an ordinary cable you can't even see, but there's always a little chip in there that's translating the serial information into something that USB can understand. Then on your computer, you can pull that serial data as just kind of Sometimes it's a TTY on Linux or serial port on Windows. So what other tools do we have here? Oh, boy.
You can move that if you want.
Yeah, we might have to move that a little bit. Let's take. Just grab it and put it in. Yeah. That's okay. What it says is logic analyzer or protocol analyzer. So what those are is they're fancy oscilloscopes. They watch the ones and zeros coming in, but they can interpret those ones and zeros in terms of whatever protocol you're using across there. We were working with an outside vendor that had designed a serial protocol to send information out from a board, and we were seeing mistakes. And we didn't know if it was us or them that was screwing this up. So we hooked one of these logic analyzers off. We captured the packet that had an error in it, and it was coming from their board. So we're like, okay, it's you. So they're great tools. There's a company called Saleae, Saleeae. Very hard to spell. They make a good one, but there's lots of other ones, and there's pretty reasonably priced ones out there now. All right, where are we at here? We're getting close to needing to be done, so I'm gonna have to speed up a little bit. So design rule number 2 is make use of the available tools. In CS, it's important that you have a robust tool set, that you know how to use lots of different tools, be familiar with them, both hardware tools and software tools, things like just grep. In my graduate school, we had a full course on tools. Just here's tools that you're going to use in computer science. Whether they're these exact tools doesn't matter, just that you understand the concept. So here's the right tool to apply to this kind of thing that you're going to be looking at. All right, so let's look at the presentation of the transport layer. So the default kind of mode is your device just sends one character at a time. Whenever it's got a character entry, it just sends it. Right. So this layer, what we're talking about is how we package up a higher level packet than that 8 bits that go across the wire, right? So what does a packet of data look like as it goes across the wire? Single character is kind of the default. It's when people go, okay, I'm gonna make a serial protocol to do this. They usually start there. Then they go, oh, it's not working real good. It's appropriate for some things, but for most things, you have to get more complicated. So you can send, every time you see a carriage return or a carriage return line feed, package up that line and you send it off. That's kind of like Arduino, I think probably uses that kind of mode, or maybe you can set it to single character mode as well. It's not great either. I've seen a lot of errors happen in that, using that kind of a protocol to send your data. So packet termination, how do you know how big a packet is? So it's kind of like the question of how you know how big a string is in a computer language. So in the C programming language, what we do is we put a special character at the end of the string. So we know that the string's done. In Java, a string is an object, and it has a length attribute. So you always know where your string starts, and you can either step through and find that terminating character, or you can look at the length and say, okay, in Java, you'd say, okay, my string is 10 characters long. So you know how far to go in memory. So you don't go trumping off in memory. Same thing with the packet. You can do either a terminating character, or you can do a length somewhere in the header of your packet, at the beginning of your packet. I've seen a lot of people not do this, and it's a really big pitfall that people fall into, and They don't know when to send the packet. They don't know on the receiving side. It doesn't know when it's got, when can I process this? Like, am I done yet? Am I done? I don't know. I don't know if I'm done yet. Another design consideration to put in here is, when you're designing at this level is, do I send clear text? Or do I send some combination of clear text and binary, right? So if I have the number 12, do I send it as character 1 and the character 2? Or do I send it as the binary representation of 12? And there's trade-offs there. If you send a clear text and you're looking at it with something like a SAILI, it's a lot easier to see what's going across the wire, right? But it's not as efficient, right? As binary.
Mhm.
If you're really focusing on efficiency, or just grabbing the data off there, you'll want to go with binary. Then you need to understand if you're doing a streaming or a transactional kind of interaction with the device. So what's the tool set we can use here? There's a library or a framework called protocol buffers. It comes from Google. It's pretty much industry standard for doing these logical data frames. MQTT, if you're using any kind of IoT device, MQTT is a very popular transport. It covers more than just this packaging, but it does cover this. Then JSON is another one that people use sometimes. And JSON is a text-based protocol buffers. You define what it is, if it's text or binary. And I don't remember how MQTT works. HTML, XML is also text-based packet. So design rule number 3, design logical packet protocol with care. So pay attention to it. Don't just run in and do the character by character thing. It also should not be an afterthought in your design process if you're designing a serial protocol. Engineers kind of like to invent their own stuff or say, oh, I can do this better. It's kind of a trap we all fall into. And what happens is, yeah, maybe it's better, but it's broken. It's the problem. You haven't found all the problems in it. And it always extends the schedule out. If you're working for like if you're at an academic place, great, go ahead and do your own thing. But if you're working for a company, they're going to want you to be done. You're always better off grabbing some well-vetted layer software and put that in. And let's talk real quick about the application layers. So if you're looking at logging some data, so one thing that people do a lot when you're logging data from a device is you'll be able to set a log level. So you can say, do I want really verbose all the logging information that's coming out of the device, or do I want just some high level information that's coming out? Being able to select different modules to report logging from. I don't want to see logging from all the stuff that's going on. I just want to see this one. Yeah, I'm trying to debug this thing. So I just want to see the output from that. And then if you're designing an app to sit on the other side of it, have filtering, have highlighting, have search, provide some facilities there to help the user. Things at this level are, they'll make the protocol easy to use or hard to use. I've seen lots of hard to use ones. It'd be great if people started paying attention to their users and doing that sort of stuff. Now, some of these things like log level and module selection, sometimes those are compile time settings. It's better if you can send it across the protocol and do it dynamically. But either way works. If you're designing a CLI, you guys know what CLI is, right? Command line interface, basically you're just typing stuff in there. Be able to display a list of the commands that you're able to satisfy. Ask for help on the commands. Be able to do command line. These are all like modern things. It's like you should be able to do these things. Command completion. History of what commands have I typed in previously. Maybe I just want to hit up arrow a couple times and hit enter instead of having to type the whole line over again. There's also, so a lot of people just assume, well, we're just going to use PuTTY for this. PuTTY is a serial terminal kind of thing, or there's also TerraTerm and Minicom. They just assume you're going to use one of those, but those don't have all the information that would be really helpful for the users to use. Okay, so RPC, does anybody know what RPC is?
Mm-hmm.
So it stands for Remote Procedure Call. It comes from distributed computing, where you have something like your host computer calls a function. That function gets bundled up and transported over to your device and executed over on your device, and then the results of that function come back. It's a programming, it's a communication paradigm, but it's also an API kind of paradigm. So if you're designing your interaction as RPC, that's your application layer. Follow general API design guidelines, provide good documentation. Some tools that you can use with that are gRPC, which is it's an RPC layer that comes from Google again. They've designed a lot of really good tools. MQTT also operates at this level as kind of a transport, a high level framework for sending messages back and forth. All right. So design rule number 4, design the application layer with your user in mind. This is another AI fun one. So I gave it clown, nerd, teacher, and robot. And it put a pirate in. I really like the pirate. Yeah, so design that application layer with your user in mind. Think about how they're going to use the system. Don't just assume they'll find a tool that kind of works. If you design it better, people will be much happier with it. And that's pretty much it. Are there any questions about serial communications or?
So how do you compare like USB and even internet and now hard drives? They're all serial communication, right?
They are, and that's where this definition of what is serial communication is kind of vague, right? It covers a lot of ground. And when I talked earlier, I said, well, here's what serial communication is, but it's not. Right? It's a little bit of a lie, but
The interesting thing is when I started in this business, like when you wanted to talk to the printer, you would go over something called Centronics, which was a parallel printer, and huge cables and all that. Anymore, I can't think of anything that communicates parallel. Almost the only word I'm waiting for processor and memory to talk to each other in serial too. That hasn't happened.
I think the only analogy is like we were talking, there's some signaling technologies that bundle up more than a single bit.
Right.
It's not a parallel, it's not truly parallel. What he's saying is we used to use parallel ports a lot more often, which you would have, if you're doing an 8-bit transfer, you have 8 lines going across there and usually a clock line as well. And there's issues with it that if you have a 1 here and a 0 here and you're switching one, it can flip. It's called crosstalk. It's expensive. The cables are expensive, the connectors are expensive, right? So serial communication has really taken over it as a generic thing. This is more of a specific, right, these serial ports that are on MCUs or talking to the USB on your computer. More specific here, but that's a good question. What's the distinction there and where are we going with that? I think we're probably going more wireless, right? But
still serial.
it's still serial, yeah. It's at a higher level, but at the lower level, at the link level and such, it's something different. It's also more complicated. You have to negotiate speed sometimes, or what type of Bluetooth are we using here, and there's complications to it. So it's not as easy as just like hopping on a serial link. One thing with serial links is you'll often have to configure both sides to be compatible. So you'll say, here's your speed and here's your configuration, that 8N1. You have to tell both sides that. There are some that'll auto configure now. It'll see the data come in and go, it looks like it's this speed, and it kind of try to figure it out. But for the most part, you have to configure those. So there's pros and cons, but for the most part, serial wins, I think.
Folks who are on the Zoom, if you have questions, you can just unmute and ask, or you can text it, and we'll be happy to verbalize it here for Mike. And in the room, you just ask the question.
Have you guys used serial ports and
Every day.
Putty? Yeah,
Every day.
yeah, exactly. So I'm sure you've seen bad,
Yeah, well, we're
Bad
using
design.
like RS-485 and 232 for large communication networks. We have like our master computer, we'll talk to up to 60 clients, 60 sensors at a time, and we'll just go through every single one. Each sensor has its own address, so we'll send the command
right,
to the address and
Right.
the command to talk back, and then
right,
we don't, the device coming back doesn't tell us, or we have no way of knowing how long that message is.
right.
We know the maximum length of the message, and so we either receive.
Yeah,
the
so you have
maximum
to
length,
wait and
or wait.
then you go, okay, I'm gonna time out here. That's where I was talking about, that. How do you terminate those packets? Cause that, all they would need to do is say, at the beginning of that packet, say, hey, this packet is 13 characters long.
Mhm.
Boom, 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 boom. Okay, I'm ready to go. I know I'm done, right?
Yep,
But
and
no,
it's a real challenge because, we have to get that data really rapidly. So I'm looping through all of these sensors as quickly as I can. And so I don't have the time to just lollygag around and wait for one sensor. It's not going to communicate. I need to move to the next. Yeah,
I
I know.
know by paying. How about you?
I use it a little bit at a high level.
Okay,
I have I'm building an application layer on top of a CAN RFID scanner.
okay,
And in order to flash firmware onto the scanner, I needed to, they have like a serial adapter, but it's not like an RS-232.
right,
I needed to buy a specific
Yes.
cable and then wire it into a serial adapter.
yes,
Then the
exactly.
serial adapter needed to wire into my USB so that I could,
Oh, wow.
it was a whole daisy chain.
Yeah.
It's like, just let me plug in a USB into.
Yeah, yeah,
It seems like a lot of industrial devices use the older.
they did. A lot of
Is
those.
that because they're worried about noise in the industrial environment?
Yeah, often they'll use what's called I think it's a 422, which is a current loop serial, which has a longer range than sort of the voltage driven. But it's still a serial protocol.
Is that what you guys use? Is that what you?
We use 422 in some cases and the 485 in others.
What's a 485? What's
It's just a slightly more modern version
Yeah,
of
I think it's the
422.
same. I think it's another current loop.
Yeah, the
technology.
big difference between the 422 and the 485 is you can have like multiple masters on a 485.
Okay.
We don't actually utilize that part, but just some of the equipment comes by default set to 485. Yeah, and our range is, 1,000 feet or something like that, some ridiculous thing. So we'll
So
have,
you have to have one of those things.
yeah, Yeah,
Oh, that's
so,
232 can't go.
no, it's like what, 25 feet or something like that.
Yeah,
And then it falls.
Yeah.
apart.
Yeah,
Then it goes away.
yeah, then you probably would want to set that parity bit and see if things are going wild. It's always the first thing we check, like, is there noise on the line? And we go check it and it's like, no, there's no noise. Dang.
Yeah.
But
What causes noise? Like having it wrapped, would that cause noise?
no, generally having a shielding cable helps protect it against noise. Any kind of other equipment that's around it that's AC lines or yeah, just any kind of fluctuating voltages.
Motors,
Motors.
nearby motors.
Yeah, motors,
Motors.
moving magnets, obviously is gonna induce currents in those lines.
Mhm.
Yeah, that motors induce a lot of noise in the systems.
Yeah, I think one of the reasons why you can go so far on the 422, I think that has two different conductors with opposing signals. And so if you have that,
Differential.
yeah,
it's differential.
so it can detect that you have noise.
Yeah, that's a good one. All right,
So if you, maybe I'll ask this question, this
Yeah.
wasn't on the list, most of the
Of course.
people who are on here are gonna study computer science and hopefully get a job in computer science. You've gone through a lot of companies.
yeah.
Do you have any advice for somebody who's getting started?
Wow, the landscape is changing really fast. There's a lot of things coming in terms of trying to drive down the cost of labor in the computer science arena. There's AI coming in. Just if you don't love learning, this is probably not the field for you because you have to be learning all the time. There's new technology all the time and you have to stay up on it. So and as you go through time, you'll start to see the patterns in the thing.